Hello everyone, and welcome to the Undergraduate's Guide to MOSFETs. In this video, I'm going to be showing you what exactly a MOSFET is, the regions of operation that a MOSFET goes through, the equations to solve for most major variables in a MOSFET, the circuit diagram of a MOSFET, and piggybacking off of that, the basic N and PMOS circuits, the channel length modulation of a MOSFET, and finally the body effect. So a MOSFET stands for a metal oxide semiconductor field effect transistor. And this is the diagram of an NMOS. And we can tell it's NMOS because of where the ends are located. They're connected to the source and the drain. This body down here is something we will go over later in the body effect, and we can essentially ignore it when we're looking at these basic level circuits. This little hashed out rectangle right here is the oxide part, and the metal oxide, and it is there so that the current is essentially zero. You can't pass current through oxide super well. We don't want current coming here in this what's known as the substrate, because it'll mess up the channel that forms here, and we essentially just want it to be zero, but we still want a gate voltage, because the voltage between the gate and the source, or the voltage between the gate and the drain, will cause a channel to form right along here. And this channel is essentially what makes a MOSFET a MOSFET. It connects the source and the drain via the gate. So the gate in source is kind of like a push button, and the push is measured by the voltage it provides. Now, we can simplify this diagram into this element right here with a D, S, and G. An NMOS, we can tell it's NMOS because the arrow's pointing from G to S. And inversely, we can tell if it would be a PMOS if it was pointing from S to G. Also, the D is usually hanging out on the bottom in a MOSFET, in a PMOS type MOSFET diagram. Now, there are three regions MOSFETs operate in. That is triode, saturation, and cutoff. Triode is where that channel really isn't formed yet, but it kind of is. There's a little bit of VGS and it's just getting up there. Saturation is when the channel is formed and everything's flowing perfectly fine. And cutoff is where there's not enough voltage on the gate to do anything, and so it essentially is just off. Nothing's happening whatsoever. It's stagnant. In order to figure out what we're looking for in equations, we have to go over the variables in MOSFETs. And what you can notice off the bat is that there's the subscript here really tells you what you're looking for in these variables. VGS is the voltage between the gate and the source. V sub T is the threshold voltage, and more times than not this is given to you as it's very dependent on the MOSFET. And VDS is between drain and source, and VOV is the overdrive voltage, which is found by subtracting the threshold voltage from the voltage between the gate and the source. Now let's move on to a bit more of MOSFET-oriented variables, not just voltage. And the first one we find is the oxide capacitance. And taking a look at zooming in on that gate that we drew earlier, we have this kind of metal bar up here, and we have the substrate down here, and this little gap in between here is non-conductive. So it essentially looks like a capacitance problem, and that's because it is. And it took a while to kind of figure out what the capacitance was coming from, and they realized that it's because these are essentially two parallel plates. And you can find their capacitance by the permittivity of the oxide and how wide that oxide is. The next one is the process transconductance parameter, which takes that capacitance and multiplies it by the mobility of the electrons. Now, once again, this is kind of like a data sheet variable, though they more times than not will give it to you. And honing in more on MOSFETs, we can get the MOSFET transconductance parameter by taking this parameter and multiplying it by the aspect ratio, which is the width of the depletion region over the width of the channel. Now that we have all of our variables in place, we have to take a look to what we're actually solving for in these MOSFETs, and more times than not, that is the current. In triode, the current is a little bit tricky to solve for. Here is the original equation, And based off the variables I gave us earlier, you can simplify it down to the MOSFET transconductance parameter multiplied all in by the overflow voltage times the voltage between the drain and the source minus 1/2 the voltage between the drain and the source squared. A lot of times when you're solving for triode, they'll usually give you the current and you'll have to solve for this voltage and you'll have to use the quadratic formula. Now, a lot easier of a equation would be saturation, and the current here, this is the original, and can be simplified just down to 1/2 the MOSFET transconduction parameter times the overflow voltage squared. But the easiest of them all would be cutoff, because if nothing's happening, no channels formed, there will be no current whatsoever. So we know what we're looking for, we know how to solve for what we're looking for, but how do we know what region we're in to begin with? And we'd have to take a look at the push button, like I said earlier, or the gate voltage in relation to the source. If it's less than that threshold voltage, no channel will form, nothing's going to happen. But if it's greater than that threshold voltage, then we know we're going to be in either triode or saturation. But how do we know which of those two? Well, then we have to look at the voltage between the drain and the source. And if that's less than that overflow voltage, then it's going to be in triode, and if it's greater than that voltage, it's going to be in saturation. If we move on to more nitpicky topics, such as channel length modulation, we see that MOSFETs have finite output resistance. If you were to put a probe here on S, you'll find that there's a specific resistance. Now, what if we wanted to reduce that resistance for whatever reason, maybe optimization? Well, the channel starts off about here, and as it's going, if we increase VDS, that channel is going to get smaller and smaller and smaller all the way until you reach S. And what this essentially does is it will reduce the resistance and it will increase the current. You have to be in saturation in order for this to work, though, because there's a channel that is formed. And we can find the new current of this channel by a similar equation that we looked at earlier. However, we're adding on this little factor right here. This factor right here, 1 plus lambda VDS. Lambda is how we change VDS, usually as a function of time, as this decreases as you go along. Or and then you add the 1 to it to get your whole new the change that you made to the circuit. The last topic we're going to be talking about is the body effect. We're bringing back this part I mentioned in the beginning diagram, and it's kind of one of those, I say nitpicky, because whenever you're learning physics, they say to ignore friction. Whenever you're learning about like flying, they say ignore air resistance. Well, in this case for MOSFETs, that would be the body effect, or the body in general. And most of the time you just ground the body in order to make these PN junctions work perfectly. However, when you put millions of these on a chip, we find that it's better to connect them to the most negative source. And what that essentially does is that makes this voltage at B less than 0. And relating that to the gate voltage, we'll find that it increases overall because this reference point gets lower, so the voltage drop between the two gets higher. And that increases the channel depth as well, which changes around our VGS and our VT. And we have to account for this by solving for that new threshold voltage before we solve for anything else, really. And that new threshold voltage is equal to the old threshold voltage plus gamma, all multiplied by basically the square root times phi sub f plus now the voltage between the source and the body minus just root 2 times phi sub f. Now these new two variables, phi sub f and gamma, are pretty much just parameters that are given from the manufacturer when they're manufacturing these MOSFETs. And they will always be slightly different because the fabrication process is no two MOSFETs are exactly the same, and it will change depending on your specific MOSFET. And these are usually given, however, you'll more than likely have to solve for VSB, but it's just a voltage difference. And that concludes our video on MOSFETs. If you join us next time, I'll be taking the MOSFET diagram and putting it into what's known as a small signal model and stepping through how to do that exactly. Thank you so much for watching.